now.
Okay. All right. So I'll pick up where I left off, and we'll finally discuss the concept of nuclearity. So here's the definition. So we say that M in solid QP is nuclear. This means that if you take, for all extremely disconnected S, if you take continuous functions on S with values in QP and tensor it with M and evaluate it at the base point, then this mapping to sections of M over S, this is an isomorphism. Or equivalently, in terms of the notation I just introduced, MTR maps by an isomorphism to M. So this was just the definition of the S-valued points of MTR. So
equivalently, any map from a compact projective into M is of trace class.
In a unique way.
Yeah. Mm-hmm.
Yeah. Yeah. So I mean, any map to M from a compact projective has a unique trace class, unique witness to being trace class, so to speak. Yeah. Right. So let me remark. Well, so both sides are exact functors of M. This is due to flatness of this ring of continuous functions. And the fact that evaluation on extremely disconnecteds is always an exact functor. In fact, colimit preserving. I mean, that implies that this full subcategory of nuclear modules, which I'll denote nuc QP, is an abelian subcategory. Closed under all colimits. Moreover, if we were to make the derived analog, for the same reason, if we were to make the derived analog of this definition, we would have derived nuclear is the same thing as each homotopy group is nuclear in the above sense. So an object in the derived category is derived nuclear, meaning if you take, well, I guess there's no need to take R-hom here, but if you take a derived tensor product here instead, and you ask that this be an isomorphism of a priori of an isomorphism in the derived category of QP vector spaces, then that would actually just be equivalent to having this condition for each homotopy group of M. So this is nice, because sometimes you want to make derived arguments with it, because sometimes it's easier to make derived arguments. So now you know that you can easily pass back and forth between them. So the characterization I want to give is, so here's a theorem. M in solid QP is nuclear if and only if M is a filtered colimit of quotients of Banach spaces.
But beware that it's not the int category of Q Banachs.
Yes. I will make this remark. Yeah, maybe I'll just say it now. So this says that the nuclear modules are so nuclear. In other words, a less precise form is that nuclear is generated under colimits. by Banach spaces. So this is a slightly less precise thing. This explains you only need to do 2 steps, yeah, quotients and then filtered colimits, and that's convenient in practice. But be careful that these are not Banach spaces are not compact. So even in the nuclear category. So, but there are many relations here. It's not an in category. So there are many relations between Banach. There are ways of writing a Banach space as a filtered colimit of other Banach spaces. A non-trivial filtered union of Banach subspaces. So actually, the structure of this nuclear category is quite subtle. So it's not an in category, i.e., it's not compactly generated. However, it is. What is it called? Aleph-1 compactly generated. So what does that mean? Well, a compact object is a thing that commutes with filtered colimits. A thing we're mapping out commutes with filtered colimits. An Aleph-1 compact object commutes with Aleph-1 filtered colimits, which are things where every countable diagram has a cone. Every countable subdiagram has a cone. So Aleph-1 compactly generated objects are closed under countable colimits. So it's kind of a bigger class. But the Aleph-1, the Aleph-1 compact objects are also different from the Banach spaces. So you have 2 more or less natural generating classes for this category of nuclear modules. You have the Banach spaces, and then you have the Aleph-1 compact objects, which I'll describe in just a second. And they're different. I think their only intersection is the like finite dimensional QP vector spaces. So so it's very difficult to describe this category sort of in what I was calling it's very difficult to give a synthetic description of this category. It's really, here you really want to view it as a full subcategory of solid modules. That's the only convenient way to define it, I think. And I don't think any category like this has really been considered before. Right, so what are the Aleph-1 compact objects? These are the co-kernels of basic nuclear modules, which are sequential colimits of compact projectives under trace class maps. Let me make another remark. And that there's a nice thing about this category of nuclear objects is that so this nuc QP is independent of the cutoff cardinal of the as long as that's uncountable, I guess. So we had this notion, we had these set theoretic issues for the category of solid QP modules. So we either have to fix a cutoff cardinal and only have our basic compact projectives involve, products over, well, essentially products over Smith spaces where the index set has a uniform bound on the cardinality, or we take the union of that as the cardinality increases on the level of the compact projectives. The nuclear category stabilizes already at the first uncountable strong limit cardinal because, well, for example, because of this description, it's generated under colimits by Banach spaces. And every Banach space, let me see. is kappa condensed.
It's not, is it?
So you can always write a Banach space as a co-limit of, this is essentially due to the fact that the QP has a countable neighborhood basis for the identity. But you can write any Banach space as a union of Banach spaces with a countable basis. If you recall, well, we had this expression of an arbitrary Banach space as a union indexed by functions, decaying functions on an arbitrary I. But every decaying function on an arbitrary I has to have countable support because of, because there's only a finite amount of spots where it's allowed to have norm 1 or bigger than or equal to 1, and then a finite amount of spots where it's allowed to have norm bigger than or equal to a half, and then bigger than or equal to 1 over n, and so on. So in total, it's got countable support. So that's where this, so that's why everything is determined by countable Banach spaces. That's why this claim is true. And then these guys are unions of products over n of ZPs. So they're kappa condensed whenever kappa is an uncountable strong limit cardinal. So that's very convenient. So set theoretic technicalities disappear on this nuclear full subcategory. Okay, so well, let me prove this theorem. Proof. First, suppose M is nuclear. So then write M as a filtered colimit of MIs, where MI are compact objects. Then, so note that, so these are quotients of Smith spaces. So note that M maps to M trace commutes with colimits. Let's go back up to the definition. Well, its value on an extremely disconnected was given by this formula here. Oops. And so, well, we're tensoring with something that commutes with colimits, and we're evaluating on the point that also commutes with colimits. So it's enough to enough to note. All right, sorry. So we write this. Sorry. When we apply MTR, we get that M is the filtered colimit of the MITRs. But then M is a quotient of Banach of Smith spaces. So S0I, S1I. And then we get that MITR is the analogous quotient of Banach spaces. Since we calculated it before, if you take a Smith space and then you take TR, you get a Banach space. So basically, this TR functor commutes with colimits. So if you want to understand what it does to an arbitrary module, it's enough to understand what it does to Smith spaces. And we just calculated that Smith spaces turn into Banach spaces. And so if you're a fixed point for this TR functor, then you are then you're generated by Banach spaces. And if you look a little closer at the precise way in which it happens, you get the more precise claim. Okay, so for the converse, it suffices to show that a Banach space is nuclear. Because again, the class of nuclear modules is closed under all colimits. But what do we need to check for that? Well, we need to take V and we need to tensor it with continuous functions on S with values in QP, and we need to compare this to, well, on the base point, at least, we need to compare this to the continuous functions on S with values in V, or which I guess, yeah, sorry, V of S. But okay, this is a tensor product of Banach spaces. So it's correct, is the usual tensor product. So in terms of, you can choose a basis for I, and then you can just, so then this, and choose a basis for the continuous functions. And then if you combine it, you'll see that you're, you know, if you combine the two bases, you'll see you're getting a basis for the continuous functions with values in V. So just choose bases and calculate. So we just show that our solid tensor product is the projective tensor product. So the basis, you know, your basis vector is just your index set for your basis vector is just multiply. And when you look at what it's doing in this case, you get exactly the claim. Okay. So let me note a corollary of this. Well, nuclear modules. So I said it's a subset of solid QP modules that is closed under all colimits. It's also closed under tensor products. And well, the proof is that Banach spaces are closed under tensor product. So that's a claim that was perhaps not quite obvious from the definition, but sorry? No, okay. All right, now I want to make a remark about a small remark. Before we move on, I want to make a small remark about the general context for this nuclearity. So, this notion of nuclearity is in general cleanest in the derived context. So if you take a good context would be, for example, C to be a compactly generated stable infinity category with a tensor product commuting with colimits. And maybe I want to say that the unit is a compact object. But we don't require that the compact objects are closed under tensor product. Okay? Is there a relation? Sorry, I'm going to answer the question in the chat because it's an important remark. Is there a relation between this definition of nuclear space and the usual definition? Yes, there is. But it kind of depends on what exactly you mean, because we're going to see in just a second that an arbitrary Frechet space over QP is nuclear. Whereas according to some definitions of nuclear, you need to have compact transition maps in this inverse system in order to qualify as nuclear. But that's kind of a feature of, or a Banach space in the Archimedean context. A Banach space, for example, a Banach space itself is nuclear in this context, but in usual Archimedean functional analysis, a Banach space doesn't qualify as nuclear. But that's just that amounts to just a difference between non-Archimedean and Archimedean functional analysis. So if you move to the Archimedean case like Peter's going to do, then they're very closely related indeed, this definition and Grothendieck's. The only real difference is basically that, you know, Grothendieck was working in locally convex vector space, complete locally convex vector spaces, which are inverse limits of Banach spaces, whereas we're using the dual things of basically filtered colimits of Smith spaces. But the two notions of nuclearity will be pretty much dual to each other. And also, yeah, but they also tend to agree on objects you put in. Right, okay. So there's a general context for nuclearity, and some of these facts hold in this context. Others not. So for example, actually this corollary, which I gave a proof using the characterization of nuclear modules, actually it's a general fact. So this, e.g. Nuclear is Aleph-1 compactly generated and closed under tensor products. That's okay. But some general characterization in terms of Banach spaces, maybe that's not okay. Okay, it doesn't make sense in the general context anyway. Right. So I was thinking of maybe giving some of the general arguments, but maybe I'll save it for the end if we have a little time. Right. So now I want to explain a surprising fact. So again, so we have these nuclear QP vector spaces inside solid, and now we've said it's closed under colimits and it's closed under tensor products. This is also closed under countable products. And let me remark right away, this fails for ZP. So again, this has to do with something special that happens when you invert P. So for ZP, nuclear ZP modules, you can characterize them very similarly. They are the filtered colimits well, the analog of unit balls in Banach spaces, so of derived P completions of discrete guys. Derived P completions of discrete modules. Well, in particular, in here you have ZP, but product of copies of ZP is countable product of copies of ZP is not nuclear.
I think that it turns out to be the solidification.
Right. So in fact, this is one of these compact projective objects. How do we prove this this fact here? So the key case again is if you take a countable product of copies of QP, the claim is that this is a nuclear QP vector space. The proof of this is so again, we take our description of we had a description of this in terms of compact projective generators. So take all functions from n to r greater than or equal to 0 of product over n and n of QP less than or equal to f of n, and then invert P. So these were Smith spaces. So the claim is can replace by its Banachification. It's oh, that's bad writing. And this doesn't change the filtered union. So this would indeed prove that it's nuclear, because then it'll also be a filtered colimit of Banach spaces. So how do you see this? Well, first of all, I already said the Banachification is a sub-object of the corresponding Smith space. So the union of Banach spaces will be certainly contained in the union of Smith spaces. So you just need to see the reverse. And for that, it suffices to see that the Smith spaces, that a Smith space when you go along in this these transition maps in this sequence, that yeah, well, suffices to see that that the transition maps eventually factor through, eventually our trace class. Or there's a cofinal collection of transition maps for this colimit, which are trace class. But you know, if you take any f of n, if you take any function f, then you can make it less than or equal to some f prime, which is defined by f prime of n is like p to the n times f. Sorry, no, I was sorry, I didn't do it in terms of. Oh, sorry. Sorry, am I getting valuations and norms confused again? No, this is good. Yeah. Yeah, p to the n times f. And then what you're seeing is the basic example. So product over n of copies of zp 1 over p, mapping to product over n of copies of zp 1 over p, given by multiplication by p to the n in the nth coordinate. And this is a basic example of a compact operator or a trace class operator. So you can actually just sort of see by hand that this factors through, that such a map when you're multiplying by things like this. If you multiply, if you're given by a diagonal matrix where the eigenvalues tend to 0, then you can just check by hand that the map on Smith spaces factors through the bonification, if you like. Okay, so that's nice. So we proved that a product of copies of QP is nuclear. So now let's do the general case. So if we take product of copies of nuclear modules, so if we write each Mn as a filtered colimit of quotients of Banach spaces, then in fact this product of copies of Mn gets to be a more complicated filtered colimit of products of copies of quasi-Banach spaces. So there is this weird, yeah, what is this Grothendieck's AB6 axiom? Is that right, Peter? Is it AB6?
Yes.
Yeah. Well, anyway, there's this funny axiom for an abelian category, which tells you how to write a product of filtered colimits as a filtered colimit of products. And it doesn't hold in many abelian categories, but it holds in abelian groups, and therefore it holds in any abelian category with enough compact projectives. So it holds in our case. So we reduce to products of quasi-Banach spaces, but infinite products are exact. So that reduces to products of Banach spaces, right? But now any collection of Banach spaces is a retract. Well, well, we can write each Banach space as a retract of a single Banach space of some huge dimension. Yeah, so we just take the maximum of the dimensions of these Banach spaces. When you increase the dimension, you're always a retract of the next guy by choosing a basis. So we might as well assume all of them are the same. So what we need is that a product of copies of a single Banach space is nuclear. But so so this reduces to, but then we had this claim from earlier, which we also wanted to use earlier, which is that this is the same thing as a product of copies of QP tensor V. Yeah, so we wanted to use this earlier. Now I can give a proof. Here's a somewhat clever argument, I guess. So we might as well, we can write V, or might as well take V to be continuous functions on S with values in QP. Then by nuclearity of product of copies of QP, we have continuous functions on S with values in product of copies of QP is equal to V tensor product of copies of QP. But this is just the same thing as product of continuous. Yeah. So this is a funny little argument, but it proves the claim.
Oh, careful.
So, what? I forgot.
You use that the internal and
comment.
the external definition of nuclearity agree.
Yes, I forgot to make that one comment. Yes, sorry. Yes, I should make that remark. So in nuclearity, we only required CSQP tensor M to be the same thing as CSM on the base point, on the point, yeah? But this actually implies the same thing for the because compact projectives.
This is an isomorphism.
Huh? Yeah. Under tensor product. All right, so we can rephrase this as the dual of a compact projective. And then we see, that for any compact projective, you have the dual of the compact projective tensor M is the same as the internal Hom from the compact projective M evaluated on the base point. Now you want to know it evaluated on a general thing, but that'll just amount to tensoring by some adjunction. That's just tensoring again with a compact projective, and then it's, yeah. Right. So you can, so this notion of nuclearity, in the general case, you do have to put the evaluation on the base point. But in situations where your compact projectives are closed under tensor product, you can do it internally as well. Okay. So let's step back and see what we've got. So we've just proved that nuclear modules are closed under countable products. And an addendum to this, on nuclear QP vector spaces, V tensor blank commutes with countable products. If V is Banach. So you also behave like a completed tensor product with respect to Banach spaces in this sense. Or actually, it's also true more generally with Frichet, but let's just stick with Banach. And the proof is, same idea. Reduces us to Banach spaces. So you have to be a little careful with the colimit argument to make sure that the form of, that it matches up on both sides, but it does. But for this, we can, for that, we can use another nice trick, which is just so we already checked that you can product of copies of QP tensor W is product of copies of W. Then we can pull that out, but then this is another Banach space, so we can put it back in at the end, and then that's the proof. Right. So it's this nuclear QP modules is a pretty magical world where the objects are not too unfamiliar. They're all built from Banach spaces, and the categorical properties are extremely nice, even with respect to certain infinite limits, so countable products. So now we can come back to Frechet spaces. So the main lemma is Mittag-Leffler. If Vn, n, and n is a system of as a projective system of Banach spaces with dense transition maps, then well, I'll write it like this: R lim 1, or as I guess it's just called lim 1. Vn equals 0. So, and I'll make sure I'm being clear. This is in condensed QP vector spaces. So there is this. So this when on the level of underlying vector spaces, so underlying abelian groups, basically, this is a version of the Mittag-Leffler theorem, which you can find in, I think, one of Bourbach-Key's books. So it holds more generally with uniform spaces, or complete uniform spaces and dense transition maps. Then you get the vanishing of the lim 1. But it's the classic Mittag-Leffler argument. So that would prove it on underlying vector spaces. But in fact, on S-valued points, you just get the same thing again. So if Vn is a system of Banach spaces with dense transition maps, then when you take continuous functions from a profinite set to that, you also get an inverse system of Banach spaces with dense transition maps, because, well, it's an inverse system of Banach spaces with respect to the sup norms, for example. But then the locally constant functions are going to be dense in the continuous functions. And then for locally constant functions, it's easy to reduce the denseness to the case of constant functions, which was the hypothesis. Okay, so basically I'm saying the Mittag-Leffler argument also works in the condensed world. Okay, so that implies another way of saying this, I guess, is that if you take the limit of the Vn's, then you get a short exact sequence with the product of the Vn's. This is this 1 minus shift map, product of Vn's, and then 0 in condensed, well, I guess in solid QP. And then, so then if you want to tensor two of these together, you reduce to tensoring all these terms together in the various ways. But now you know that products of Banach spaces, so you reduce to, if you take a product of Banach spaces and tensor it with another product of Banach spaces, you can take the same one again using a trick. But again, this you prove using the same trick. So product NV is the same thing as V tensor product NQP, and product NW is the same thing as W tensor product NQP, QP. And then when you tensor these two together, you get V tensor W tensor product of copies of QP tensor product of copies of QP. But we calculated that product pulls in. So therefore you deduce it also for Banach spaces. Okay. Yeah, if you try to calculate directly the solid tensor product of two Frechet spaces, I mean, well, maybe it's just me, but I think you start to go very, very crazy. So you really have to. So these techniques here are actually quite useful. These reduction techniques. So I have 20 minutes left. I want to say a word about descent. So. Another, I think, kind of shocking application of this of these nuclear modules is you get a very general kind of descent theorem. So let me just phrase it. I'll state it right away. So, well, okay. Well, first of all, let's say that A is is a commutative algebra in nuke QP. Then we define nuke A to be A modules in nuke QP. Okay, so that makes sense. Let me make a remark. You could also look at A modules in solid QP modules and redo the nuclear discussion. There. The result would be the same. I won't get into why, but okay. So so let me state a theorem. So suppose A to B is a map of algebras in nuke QP. Suppose of two hypotheses. So one, suppose that the tensor product from nuke A to nuke B has finite Tor dimension, Or I should say, so B has finite Tor dimension over A with respect to the relative solid tensor product. And second of all, that for M in nuke A, if M tensor A B, sorry, now I should pass to the derived category. Sorry. Let me write NA for the derived analog of so if you look at the derived analog of, so this is now an infinity category, stable infinity category. So I just want to, so I look at objects in derived solid QP modules whose homotopy groups are all nuclear, and I take A modules in there. So it's probably the derived category. NA is probably the derived category of nuke A, but I don't want to think about whether that's the case. Right. So so suppose two for M in NA, so, if M tensor AB is connective, then so is M. Then you have descent. So for this script NA, so the script NA is the same thing as the inverse limit over the cosimplicial diagram of NB tensor AB. Right.
Where all tensor products are derived.
Where all tensor products are derived. Yes, thank you. Yeah. Right. And furthermore, you can extract some more concrete consequences from this result. So if you're only interested in the underlying discrete ring, so perf A, perf A evaluated on the base point, this is also the same thing as you also get descent for perfect complexes. Perf B evaluated on base point, perf B tensor AB evaluated on a base point, and so on. And let's say if all B tensor, well, if B is flat over A, just so I don't have to write derived tensor products and explain what vect means in that context. Also for vector bundles. So the main example of this is, so if you're given an A naught mapping to B naught, map of p torsion-free rings, which is flat mod p. Well, p torsion-free p complete rings. Sorry. So then we can recomplete in the condensed world, and then so if we take A0 1 over p to B0 1 over p, so we make sort of this is kind of like a user unit balls in a Banach algebra. Then we make the corresponding Banach algebra. Faithfully flat, yeah. This satisfies the hypotheses. And then the conclusion is a theorem of, well, the conclusion for perfect complexes and vector bundles is a theorem of Drinfeld for Vecht and Akil Matthew for perf. So these are, so these are, I mean, these kinds of things come up in, if you're doing descent for vector bundles or perfect complexes in rigid analytic geometry. And that's a very special case of this, where you start out with just a map that's faithfully flat mod p, but that's a localization mod p. And then Drinfeld made this observation that you don't need a localization and you don't even need any finite type hypotheses. You only need, it could be a very wild infinite thing, but as long as it's faithfully flat mod p, you still get this descent for vector bundles on the level of the rigid analytic generic fiber. So these are kinds of things which, it's a little involved to prove them. You can read Akil's article or Drinfeld's article, for example. But I think this nuclear framework gives a very appealing way to attack them. So let me explain a little bit about why. So it's a sketch of proof. So you use this general Bar-Beck criterion. So you need that that this is conservative, and say commutes with geometric realizations. And the conservativity is not too difficult to prove using the second hypothesis, and maybe actually the first hypothesis as well. So this second hypothesis is telling you something like conservativity. So if your homotopy groups vanish in negative degrees when you base change, then they have to vanish also there, and then that shifts to statements about homotopy groups in arbitrary degrees. And
right, why do you need part one for this?
Maybe you don't, but I think if you want to make, maybe if I remember correctly, you have to be careful with the argument and passing to the limit in one direction or the other. But maybe I'm mistaken. Yeah. So. But the place you really seriously use part one is, so you might think, so a geometric realization, this is a countable limit. Namely, it's in fact, you can make it a sequential countable limit. So it's the inverse limit over n of the partial totalizations. So the limit over delta n, truncate the simplex category to dimension n, and then take a limit over the tower of that. And this can be always resolved by infinite countable infinite products, because it's yeah. So you might think that we'd be okay by the fact that we know that countable products commute with tensoring with Banach spaces. But we have to be careful because this is a relative tensor product. And a relative tensor product is also a geometric realization of things. well, okay, let me say geometric realization of you know, absolute tensor products with absolute tensor products. And we won't be able to commute, okay, let me just say the issue is that, so if this guy were connective, then there would be no issue making the argument with a relative tensor product with the Banach space commuting with the infinite products. But since it goes down in homotopy, you need to be able to control the Tor dimension in order to make a conclusion about arbitrary. So even if X were connective, when you take this partial totalization, it goes down in degrees. So you need to be careful with that. And that's where the first hypothesis comes in. But then, yes, but anyway, the essence of it is true. And it's this fact that these nuclear modules are closed under products that lets you make this. So this argument in the end is very short. And it's just nuclear modules being closed under products and tensors with Banach spaces commuting with those infinite products. And then you just have to take care with the homological arguments passing to the limit. So in the end, it's actually quite simple to prove, given what we've discussed. The other interesting thing that I want to talk about is how do you get such classical consequences?
I mean, this condition 2?
Yeah.
Could you replace condition 2 just by the statement that it's conservative?
No, no, I want to get the vector, for the vector bundle conclusion, I need something like this, I think.
Okay, but if you only want to get to perfect complexes and for
Yeah.
nuclear modules, then you wouldn't need it.
Yeah, that's right. Yeah. Yeah, I could also just say it's conservative. Then I just wouldn't know how to get this last statement. But okay. Yeah.
No, but I think you get that anyways.
Oh yeah.
I think so.
Okay. Yeah. I'm not shocked to hear that, but I'd love to know the argument. Yeah. So anyway, Anyway, this is I guess a mild generalization. Yeah, well, it doesn't matter.
No, you can. Yes, you can. Yeah.
Okay, great. Yeah, but I think in practice you check conservativity by checking something like that anyway. But yeah, that's good to know. Okay, so so we have these nuclear modules. Right. Well, let me take. Here's a general result. In other words, it holds also in this abstract framework that I was discussing earlier. Then if you take something nuclear, which is also compact, now let me work in the derived category. So I work in derived category for simplicity. If you're nuclear and you're a compact object, that's exactly the same thing as being a dualizable object.
In which generality?
Yeah, this generality of the stable infinity category is compactly generated.
All right.
Yeah. Okay, and then right. So this is actually quite easy to see. I mean, if you're nuclear and you're compact, so nuclear means a map from a compact object always has a unique trace class representative. So if you're compact, you can apply that to the identity map. So this has a trace class representative. So that gives a certain map from the unit to the dual of X tensor X by definition. And if you just trace everything through, you'll find that this is the co-unit for the duality datum, proving that your X is dualizable. And for the converse, since we assume the unit is compact, it follows that any dualizable object is compact. And then it's also going to be nuclear. I'm forgetting why, but it's some very simple reason. Oh yeah, because the identity map is trace class when it's dualizable, and then it's the sequential colimit of the identity map along itself. So it's one of these basic nuclear modules, if you like. Okay. But then there's also an additional further argument which gives you control over what these dualizable things are. and this is generated as a fixed subcategory, or generated by cone of 1 minus f m, where this is a compact projective. So now I might have to be assuming some T structure in my general situation, but anyway, we can specialize to the solid QP if we like. So this is a compact projective module, and F is trace class. So this is this is a nice little argument, I guess, that I probably don't have time to give. Why? So if you want to understand what the dualizable things are, then it's enough to analyze just this two-term complex of compact projectives. And then the claim is, for example, just to give the simplest example, oh, wait a second. Oh no, I'm so sorry. I'm so sorry. Yeah, sorry. If the argument works. So, sorry. If A and B are Fredholm. Yeah, sorry. I forgot this.
Well,
I really
you need it if only for A you need it, I guess.
Only for A? Are you sure? Okay, well, maybe, but okay. Yeah, I'm sorry. I should have put this in the example. So in the example, you can also verify an extra condition on A and B, which will imply that you can deduce these statements from this statement here, these statements from this statement. But I shouldn't have claimed it in the general case of A, B arbitrary nuclear algebras. So what do I mean by Fredholm? QP, for example, is Fredholm. Any such two-term complex is discrete. Meaning discrete relative to QP. So in other words, if you take, so let's call this X. So if you take the underlying QP vector space and then tensor it with the discrete QP up to the condensed QP. So in other words, this is some direct sum of copies of QP as an abstract vector space, but then you make the direct sum of copies of QP in the solid world instead. Right, so any such cone is discrete. And this implies that since it's also a compact object, it will then have to be a compact object in the discrete world. And that means it's a perfect complex of QP modules. So it's just a finite length complex of finite dimensional QP vector spaces. Right. So that's this Fredholm property. So if you can check that any such thing is discrete, then you will deduce that dualizable is the same thing as perfect. And it's kind of formal that dualizable passes through these inverse limits. So so if you have a statement like this, you get it for dualizable objects as well, just because these are symmetric monoidal functors. And that gives it for perfect complexes, and then you get it for vector bundles. So by the way, checking that this is discrete, this is a version of this, the reason it's called Fredholm is it's a version of this, I said that these trace class maps are kind of like compact operators in standard functional analysis, and it's a well-known and widely used lemma that if you perturb a compact operator, if you perturb the identity map by a compact operator, you get what's called a Fredholm operator, which is in particular has finite dimensional kernel and co-kernel. So this is kind of a generalization of that. And actually, this is not so difficult to prove that these two-term complexes like this are discrete. I don't have time to give the argument, I think, but the point is this. You're reduced to checking something over ZP, but you have to replace 1 by maybe some power of P. And then you want to check that the map from the discrete guy to it the map from the discrete guy to it, you want to check that the cofiber has bounded torsion. And to check that, it's enough to get a uniform bound of the torsion on the mod p to the n reductions of this p-complete guy. But then you're in the discrete setting, and it's very easy to analyze what's going on. And you'll find a bound of exactly this p to the n for the torsion in the discrete case. So it's not a very long argument. I was hoping to be able to give it, but I see that I'm out of time. So I'll have to leave it unexplained. So thanks, guys.